Our speaker today is Dr. Neven Simicevic. He is currently professor here at Louisiana Tech University in the physics program. He did his undergrad and graduate work at the University of Zagreb in Croatia. He did his undergrad in theoretical physics, whereas his grad work was more in experimental nuclear physics. He did his thesis work in Germany and Switzerland. Then he came to the US for a postdoc, first at MIT, and then at the University of Illinois, Urbana-Champaign. And then he found himself here in Louisiana. Better winter weather, I guess.
Well, we all did.
Yeah, exactly. Yeah. We all end up at the same place, like a state function. All right, so with that, please join me in welcoming Dr. Simicevic, where he's going to tell us about how they built the bomb.
Yeah. This is the third seminar of the series. It was suggested by Lee Sawyer that because of this popularity of Oppenheimer movie, that we should maybe discuss a little bit and give some insight of physics. At that time, there were already two seminars by Lee and Eliza, and this is going to be the last one in the series. So, when I was a student, they just finished building a nuclear power station very close to my university. If you can read here, I studied in Zagreb, University of Zagreb, and nuclear power station was built in Krško, which is 36 miles away. And so because of that, we kind of had a very good nuclear reactor program at our university, which was part of the physics department of the College of Electrical Engineering. So I took my classes in nuclear reactor physics at College of Electrical Engineering. What was very interesting at that time is that United Nations were looking for two inspectors, and they decided for Yugoslavia to provide, and they decided that one inspector for United Nations nuclear power should be from Zagreb and one from Belgrade. And I liked this job. I was just graduating, and so I suggested to my advisor that I would like to become inspector for nuclear proliferation, and to get that you have to go to the in Vienna 2 years in the school. But my advisor said, "Oh, colleague, you are too good in physics to be inspector for nuclear physics." And so I stayed in ordinary physics instead of becoming a member of United Nations. So all the work which I'm going to present here is the work done by other people. I don't claim anything here, and this is only for educational purpose. So, how did it all start? How did we start thinking about building a bomb? Every discussion of nuclear bomb starts with this multiplication factor K, which typically says how many neutrons you have in next generation compared to the number of neutrons you have in previous generation. And if this factor, so if you produce more neutrons in the next generation than you had in the previous generation, if this factor is more than 1, you have a supercritical situation. If this factor is less than 1, you have a subcritical situation, in which case the number of neutrons will slowly decay. In the previous case, the number of neutrons will grow, and if your K is 1, so if the number of neutrons stay constant, then your neutron population will stay constant. And so what you want to find out in nuclear engineering, you want to find out what is the critical mass for which the number of neutrons is the same. And this is a problem which was probably studied from the time when neutrons were discovered. That's about this. And this is the work by the first presentation of the critical mass done by Oppenheimer. As you can see, the Oppenheimer published this formula which calculates the critical mass. this formula estimated with the data they knew at this time for the cross section, this formula estimated that the critical mass for uranium-235 would be about 200 kilograms, and from the density theory, and it will be 60 kilograms from the integral theory. Another formula which was shown here is that if you put a temper around, so if you put some reflecting material around the mass of the uranium which you need for the bomb will go down by about factor of 8. This formula is correct. So even in 1943, this formula, which now you can use it to calculate the critical mass, was complete, and it didn't change like till today. We still use the same formula for the calculation. So to understand, and this is because we are looking for the historical perspective, to understand what physicists knew at that time, I will give you some steps to discuss their education, the laboratory they were using, and so on. So let's start by discovery of the electron. In 1855, German physicist Heinrich Geissler invented vacuum pump. And the vacuum pump allowed, which means he managed to reduce the pressure of the air in this bulb to about 0.001%. Immediately, the physicists start doing experiment with the vacuum tube, and by connecting the ends of the tube to the batteries, and what they found out, done by Julius Placher and his student John Hittroff, they found out that if you connect to the battery, you will see some kind of pale green color around on the windows of the tube, and they start thinking about what causes this color. In 1897, Joseph Thomson did a little bit more experiment with this green light, with whatever produced this green light by simply putting these rays through the magnetic and electric field, and he found out that this light is produced by rays which have a charge, they have a mass. They studied this in many details, and this was the way how the electron was discovered. You can see that what I show here on this image is this is in 1897. Those people who discovered the bomb, they were working in the labs like this one. So this is how the labs looked before the bomb was discovered. I'll show you some more picture related to how the places where those people got their education. In 1895, German physicist doing the experiment with these cathode rays, he didn't still know that those are electrons. He accidentally discovered X-rays. And here is the lab he was using to discover X-rays. So this is 40 years before the bomb was discovered. The lab looked something like this. And in physics, people don't get new ideas. Ideas develop slowly. So people always try to work on the project or expand the project which already existed. And this is like, for example, Röntgen discovered X-ray accidentally by looking at trying to understand electrons. Now we have Antoine Becquerel, who discovered radioactivity by trying to understand X-rays. And it was also by accident, And because what he found out is, in addition to like X-rays being produced by the electrons, he found out that some elements spontaneously emit unknown radiations to him. And they start now studying this. And particularly well-known people who study this radiation coming out from elements like uranium, thorium, actinium, it were Pierre Curie and Marie Curie. And again, we are coming closer and closer to the time where the bomb was discovered, and you can see the labs still look the same. So even 40 years of the labs in which people did experiment look very similar to the labs years before. In 1903, Ernest Rutherford started now studying this radiation, and he found out that you have 3 types of radiation coming out from the nucleus, which today we call alpha, beta, gamma. He called them alpha, beta, gamma because he didn't know how many there are going to be. So he assigned Greek letter, and he ran out, he only needed 3 letters. And the way how he distinguished them in his lab, which I'll show you a little bit later, the way how he distinguished them was by simply looking how much material you need to stop them. And he found out for alpha, you need very, very tiny amount of aluminum to stop it. For beta, you need a little bit thicker aluminum. And for gamma, you need even more thicker aluminum. And as I said, the classification he gave to those radiation was based on penetration through aluminum. Later, people now learn how to deal with electron, looking how the electron goes through magnetic and electric field. Did the same experiment, and for next few years, they managed to find out that alpha particles are nothing but 2 protons and 2 neutrons, that beta particles are electrons or positrons, and the gamma rays are nothing but electromagnetic radiation. So, as you can see before, people constantly try to expand on the work done by other people. Once the alpha particles, beta particles, gamma particles were discovered, people now start using them to figure out something new. So this is the next step. And this is a Rutherford lab. At the time, he was trying to figure out what those alpha beta particles are, gamma particles are. And again, this is the lab on the beginning, as you can read, in 1905. This is the type of where people did experiment. And now, as a next step, so now you have alpha particles, you have gamma, you have beta. You can now use them to do additional studies. So what people did, and in 1911, based on the experiment by Geiger and Marsden, what they found out, if you take alpha particle now as your beam, and you scatter them on the gold, on the foil, they used gold, they found out that most of the alpha particles will go through the gold without doing anything. Some of alpha particles will scatter forward, and very few will scatter completely backward. And so what does this mean? Whatever is made here of gold is very small, because most of the particles do nothing, and it's very heavy. So it's heavier than alpha particles, otherwise the alpha particle could not recoil back. So this is very, very, as you see, using the discovery from before to find out new things. And this was discovery of atomic nucleus. And you can see the lab in which atomic nucleus was discovered was again in the Rutherford lab, and this is how it looked in early 20th century. So this is now as new things were discovered, new other things were consequence of previous discovery. This is very interesting period of time. If you really look in 1911, when nucleus was discovered, till 1932, I show you the neutrons. When neutron was discovered, this was a period where people really didn't have a clue what's going on. They could measure the mass of the nucleus, but it did not fit with the charge assigned to the proton. So you need to have something more in than just protons. One of the ways to fit the mass and the charge was that you assign to every nucleus positive charge. Now, in order not to have too much positive, you have to put inside the nucleus certain number of electrons so that you have the right charge. But the problem with putting electrons in the nucleus was did not agree with Heisenberg principle, and it was really very confusing time. To really papers from that time were very interesting. All kind of model people were thinking about how the nucleus look in order to kind of make a charge and mass of the nucleus agree. And this was solved in 1932. In 1932, James Chadwick discovered neutrons. And the way how he discovered neutrons is simply, again, he used alpha particles to hit beryllium, and then he realized that there is nothing he can observe in between, and so whatever was here must have been neutral. Once to hit the paraffin, it produced protons. And he simply, with this experiment, has discovered neutron. And this is typically drawing you see on the slide, and this is this camera, this chamber here, used to discover the neutron. And this was one of this is why he got immediately Nobel Prize just in 2-3 years after. And his paper on discovery of neutrons, which was published in Nature, was 1 page. And this by now knowing that the neutron exists, this really solved all the problems with the nucleus, many other problems, and this was really one of the discovery. As you can see, the neutrons was discovered in 1932, 10 years before technically the work on the bomb has seriously started. And again, this was one of the, probably in the history of science, one of the biggest and fastest developed ever. In 10 years, going from the type of the work done in this kind of labs to the work done later in Los Alamos. And I will, this is very interesting also. I will explain certain things which happened in very, very short time. What's very interesting, in 1933, Leo Szilard make idea that you can actually make nuclear bomb. This was before the fission was discovered, because he said, if we have material which will emit more neutrons than just one, if such a material exists, he didn't know that this material existed at the time in 1933, that we can make self-perpetuating nuclear chain reaction, which means we can make, he was thinking from the point of producing the energy, he was thinking we can produce enormous amount of energy out of this type of reactor. So this was before fission was discovered. Enrico Fermi, and you see, there is always the same pattern. You see, now when people discover alpha particles, they use alpha particles to do experiment. When now they discover neutrons, they start using neutrons as a beam to do the experiment. And in 1934, Enrico Fermi in Italy, he was still in Italy at the time, he tried to create a new element, transuranium element, by using neutrons, and he discovered fission, but he did not understand what's going on. He found that, yes, he produced new elements, but he didn't know what those elements are. 4 years later, in France, Irene Joliot-Curie and Paul Lesavich did experiments which technically first time proved the fission, and they did everything right, but they mislabeled the final product. They give the final product wrong. They didn't know what it is, wrong element. And it was never accepted as a serious discovery just because of that. Otto Hahn and Fritz Strassmann copied their experiment, but they were better chemists than they were, and they really find out that what the right element which come out of after this splitting of uranium, and this was now called discovery of the fission. It happened that my professor, who got a PhD by Heisenberg, he was a Göttingen at the time when Otto Hahn and Fritz Strassmann discovered fission, and he said they were having a seminar like we have at 3 o'clock afternoon in Göttingen every Wednesday, and in the middle of the seminar, someone entered and said, Otto Hahn discovered fission. And there was a silence. He said, I thought what he said. There was a silence at the seminar, and after like 10 seconds, someone in the back said, wow, we can make a big ball. And that was the first sentence said in Göttingen about fission discovery. I don't know, maybe Leo Szilard said it. He was also somewhere. All these famous physicists were in Göttingen at that time, including Oppenheimer, who was there about 10 years earlier. And now, once the fission was discovered, now other people try to do experiment with the fission too. And Frédéric Joliot-Curie, husband of Irene Joliot-Curie, and Halban and Kowalski, they found out that in some cases, when you do fission of uranium-235, you can produce more neutrons, and they found that they can produce several neutrons, and therefore you can have a possibility to make this self-sustained chain reaction. Things which were predicted 1933, Leo Szilard, before he even knew that fission is, and not that fission is possible, but the fission with the products which will produce more neutrons will produce more neutrons, that this is actually possible. Fermi ran out from the political situation in Europe, came to the United States, and immediately used this production of more neutrons, immediately use it to build first a nuclear reactor, and this was in December 1942. So you can see in 9 years from prediction about possibility that you can use fission, which still was not discovered, we created the nuclear reactor. I mean, such a technology, a development technology, I don't think ever existed in the history in such a short time. This is Szilard's reactor or bomb. You see, he designed this in 1934, and he said, like, use deuterium target to produce neutrons, and now those neutrons can start a reaction in this feasible material if it exists, and you can now have a water cooling, because he was thinking about producing energy out of this rather than making a ball. So you see, he said we can do something if only he knew what elements might behave this way. So he didn't know, but he came with this idea in 1933, 1934. This is, again, one example of the laboratory. This is Otto Hahn, the table at which they did experiment. It's arranged to look like where they really did fission experiment. You can see the technology at that time. So this is 39. This is the same technology later used in Los Alamos, and you can see vacuum tubes, you can't call it electronics, but what they were using to measure and find the data. So this is the example of technology, which is used to actually build the bomb. Here you have example of one of those are historical images of the nuclear reactor built by Fermi. It was built by uranium and by the carbon as a moderator, and what is very, which I'm going to say later, they didn't know much. They thought they know more than they did, and you can see, although Fermi was confident that it could control the experiment, he was confident. He was not 100% sure, but he put stationed 3 graduate students, which he called Suicide Squad, with on the top of the reactor to pour bucket of cadmium solution of the experiment in the case the experiment failed. So those people were there because they simply didn't know. And I'll show you later that they didn't know much. And now to the standard, which more or less everybody knows. I was talking about this, how was this historically discovered, and so. And now after you discover this nice color graphic, you can present what is actually happening. So fission consists of incident neutron hitting fissionable nucleus, which in our case is uranium-235, and after they absorb it, this nucleus becomes unstable and splits in 2 other elements. They don't need to be always the same. And in this process produces 2 or 3 neutrons. And those neutrons can now hit next uranium and produce even more. So this is how one can imagine the neutron, the fission, the chain reaction.
So, Neven, a technical question on that slide. The particles on the right look like fission products. So are they uranium or the fission products?
They're uranium. Those are uranium.
Yeah, but they're actually the bottom middle figure.
Ah, that's a good. Oh, you notice this. You see, this is the result of copy and paste. When you are lazy to do this right, and you just copy and paste, and but a good. I didn't notice this. I was concentrating on physics, not graphics. And so, what is nuclear fission? Has it will produce chain reaction if those neutrons, every of these neutrons will hit uraniums and produce more neutrons and so on. But it won't happen like this, because some of the neutrons will simply escape. And this is what you have to take into consideration. So if you have, if you start reaction, the neutrons that escape from uranium do not contribute to fission. So you, to make sure that uraniums, most of the neutron will stay inside, you calculate the critical mass. and this is what critical mass is. And only in that case you will have a chain reaction. So if you are subcritical mass, more neutrons will escape than the neutrons which are produced, and things will not exponentially grow. So you will have simply or decay or less stable situation. Here I hope it will work. So here is an example how this actually works. So let's assume I will make a concentration of uranium a little bit more. And let's say you have one neutron, and you will see what's going to happen. How does this chain reaction work? Let's run it. Wow, not much has happened. So let me increase the number and run again. Still, this is what happens when you are subcritical. There is no critical mass. I'll increase this a little bit more. They are not going to stop. Here it is. You see, half of the uranium was hit, reacted with the neutrons and produced neutrons, but half did not. And this is again a situation which clearly show you how the number of uranium, or what we say critical mass, it's important. So now, just to finish this, I'm going to put as much as I can. And
sound effects.
and that's it. You see this. Okay, still have some survival here, but this is the kind of show of what do we mean under critical mass. And now we'll come in the situation that is the bomb possible? Szilard never talked about bomb. He was talking about nuclear reactor. But after some time, he was convinced that you can make a bomb. And they were very much afraid that the Germany will do this first. So what has actually happened is that Leo Szilard approached this businessman. This is Goldman Sachs, very, very rich guy. And because he had the connection with the President Roosevelt at that time, he asked him, Szilard asked Sachs to contact Roosevelt and explain to him that you can actually build a bomb. Sachs said that they don't have very much argument to do this because who are they? And then they said, okay, if we ask Einstein to sign our letter, then it will have a little bit more weight. And Einstein signed the letter who he did not write at all. It was written by Leo Szilard, and he signed this and now put some kind of weight to it. So you can, as you can read here, Szilard came with this idea. Sachs suggested that they get Einstein's signature because of his fame to then give it to Roosevelt, and he was now convinced, and he created advisory committee on uranium. And you see, first time in 1939, and this advisory committee of uranium become Manhattan Project. And what is very interesting, I mean, that's another topic. Being in physics for so long time, I start doubting that Einstein actually did anything. I really doubt. If you really look at Einstein, his Brown motion was work of his wife. His wife was working. Special theory of relativity was discussed in the bar he was going after the work with a physicist from ETH, so he just reported it. Already there they discovered. General theory of relativity, he did it wrong. And he was presenting Göttingen in front of Hilbert, and then Hilbert's students corrected his theory and said, if you want this theory to be right, it has to be like this. And then he sent the letters to Hilbert and said our theory, but later he published under his name only. And finally, he signed the letter. He did not write at all. I mean, how can you do this? I mean, how can you say, yes, I'll give my weight, but that you signed the letter you did not write? That's so now you start thinking about how many other things he signed. Oh, another story. It's that his son, he hated his son. He hated his first wife. And his son asked for money, if he can help him. And Einstein said, in his letter, he said, I'm so famous, you can just cut my signature and sell it. This is the all in the. Okay, so now of course you said how I'm going to build the ball, and I go back to Oppenheimer page in 1943, and I said this formula is correct. It's not wrong, and the reason why I'm saying it's correct is because, as I was reading about, Oppenheimer was very bad with math, and his formulas were always wrong. It always missed factor of 2, pi, something, and so always other people had to check it. And I don't know if he did it or someone checked, but this formula is correct. Now, what does this actually tell? People always talk about critical mass. And always say in the mass, but it's not really critical mass, which is important for nuclear reaction. It's actually critical volume. So what you see in this formula, and I'll come back, is these several numbers here, which is nothing but chemistry. This is when you change numbers of atoms into mass. It's whenever you see Avogadro number somewhere, this is what the Avogadro number does: change moles into grams and so on. And so this is this part here of the formula. This part here is a critical radius, because what you actually calculate is a critical radius, not critical mass. You just transfer the mass in the radius. Critical radius, one can immediately say, depends on the geometry. So this radius here is calculated for sphere. If you would like to calculate the critical radius for the cylinder, you have another formula. In reactors, we do calculate critical radiuses for cylinders. In making a bomb, they did it for sphere. Later, they changed it in the cylinder. So this is from diffusion theory. This is now clear copy of this is the critical radius from diffusion theory. But diffusion theory was calculated under assumption that the material is infinitely big, which is not physical reality. So you have a correction on infinite, which is this part here. So this is the correction of your diffusion theory. And everything together, as I already said, predict critical mass of 200 kilograms. If you just use this part, and predict 60 kilograms if you correct for this finite volume, not infinite volume of the material. Now, since we mentioned that this is done from the diffusion theory, then what people knew at this time? So this is from the same meeting in 1943, and the guy who was responsible for diffusion theory was Hans Bethe. I had a chance to be at the seminar of Hans Bethe in 1992, 91 at MIT. He came as an old guy at MIT, gave us a seminar. It was much more people than today here. And you can see he gave here some hint of how you calculate. So this is the critical radius you get solving this differential equation. And since this is very, very easy, I'm going to give you some things how they did. Because finding the critical radius is probably the most important part of all this calculation. And so how it's done. And once you know how it's done, then you understand what they did. So this is diffusion equation, which simply calculates some flux as a function of position and as a function of time. And this is a standard diffusion equation.
Is this going to be the test?
It's, yeah. And now, this is for students of mine who are in math methods, they know immediately if you want to solve this equation, you have to do it by separation of variables. This is what they did. So once you separate the variable, you get this radial part here. And time part is equally important, but I will not do time part now yet. So this is this equation. It's a Helmholtz equation. And those are parameter coefficients which are used in the equation. Everything is explained here. So when this equation has very simple solution. It's A over R sine BR, C over R cosine BR. And so now you apply boundary conditions. The boundary condition number one is that at the zero, at the center, the flux cannot be infinite, it has to be constant. So if you put 0 for R, this part is 0 because sine of 0 is 0, so you don't worry about this part. Cosine of 0 is 1, 1 over 0 is infinity, so the C has to be 0. So this how you solve. So you now have only this part here. So now you want this flux to be 0 for certain radius R. So you look, what is the condition on this radius R, which we call critical radius, so that the flux is equal to 0. And you simply put this to be equal to 0. You get this equation because sine is 0 for n time n pi, and you put this in your formula, and out of all n, you only choose n equal 1. Other than you don't care. So this coefficient is simply pi over R squared, replacing the meaning of this coefficient here. You get this formula, and putting all the parameters in, you get your formula for the critical radius. So this is really straightforward, which one can do in math methods as a graduate student. And this is the formula they found from diffusion, solving diffusion equation in 1943 or before that. So this is how you solve.
Neven, just a small correction, that sine R over R at R equals 0 is actually 1. It's the first Bessel's function.
This.
So finite flux. No, cosine, you're correct. The first
Sine of R over R.
Yeah.
The limit is 1.
limit, take the limit to R equals 0 and you get 1. It's the
Yeah,
first
so this is not infinite.
No, yeah, you said it's
So
zero,
this is
right?
not infinite, this is infinite. So C must be
That's
equal to
correct.
0.
And the second term you're correct.
And this is, so you can see our calculation of critical radius is part of the equation for critical mass by Oppenheimer. There is this correction here, and this correction is also easy to find. It's simply you don't assume that your material is infinitely long, you assume infinitely big, so you assume that it's a constant volume. So you add to the previous equation, you add that your density goes to 0 as a certain function. And this is then correction you get, which is this correction here. And this is what you have, this is those equations, equation for critical mass and equation for critical radius. So what people actually calculate, I said critical radius, not. So they were very, very lucky, because with what they know, they found out critical mass, as you can see, 90, 40, 41, 41, 41, 43, 43. It goes from like there is no critical mass, or critical mass is almost 0, to 10 kilograms, like 40 kilograms done. Then Compton calculation was also like almost 0. Oppenheimer calculation was the 60 kilograms. Bethe calculation was 80. And so all these people at that time had a different mass. So they didn't know exactly what the critical mass is. And the reason why I didn't know is because of parameters they were using in calculation. And you can see the most important things they need to know in order to apply this, calculate this diffusion was the parameters which go in this. So they need to know all the cross section which are there, and you see discussion of fission neutron spectrum. Those were numbers which at that time many people tried to measure, and they were discussing at that same meeting about the coefficients. And here they are. Now you see, in order to calculate the mass, critical mass properly, you have to put cross section for fission, the number of multiplicity, how many neutrons are produced in one reaction in average, and let's say cross section for transport. So what is the probability that the neutron will go out? And you can see that in 1940, 1943, those cross sections were very different. Multiplicity went from like less than 2 to 3, which is very important. A factor of 3 in that formula changed mass a lot. And transport cross section also, you see, this line is today what we know today. And you can see how the data were scattered all over. And another things which you can see at the same letter is that if you use temper, so if you use a reflector, neutron reflector, you can reduce the mass to by roughly factor of 8. So it will be like 25 kilograms instead of 200 kilograms. And of course, they immediately decided, because of the reduction of the material, to use a tamper around the uranium. So this is how you calculate the tamper, same thing. So this is example. This is the calculation with the tamper. So what you do, it's the same diffusion equation. You have a core, which is your uranium. You have a tamper, which is a reflector for the neutrons. And you have to solve the same diffusion equation like the equation before. So it's the same diffusion equation, and with a different, so it's a similar like previous, so the solution will do, you'll repeat everything. With the separation of variable, you get the same. But this time you have to use this boundary condition. You have to say the number of neutrons at the boundary between two materials is the same, and the flux is the same. So these two boundary conditions I use on the same equation as before to find out the effect of tamper to build the bomb. And that's it. So as it's written here, you get a reduction of critical radius by factor of 2, which means the volume is reduced by factor of 8. How to build the bomb? You can see the sketch from 1943 they immediately thought about, if I have two subcritical mass and I project this missing part in, I'll create the critical mass, and this critical mass will explode. So that's that. And you see, even at that time, there was a tamper shown here around uranium. How you build it a little bit in more details. So what you do, you take a cannon barrel. You keep uranium target, and that's a real how they did it, as a piece of cylinder, and you have a uranium projectile, which is like a cylinder with a hollow cylinder. And you have conventional explosive here. And there is a cannon barrel to ensure that the explosive, the things will go forward. So they use the standard cannon barrel. And so this now goes here, create the critical mass, the tamper is around, and these things will explode. This is the design what they use. There is this, I said I will not discuss time-dependent diffusion equation. I just give you the result. Once this piece start going over, you start creating critical mass. But this critical mass will produce enough pressure that things will start blowing away and you will lose critical mass. So you don't want to use, so you say the time required, the fissile material, is what you find from diffusion equation. Then you have time to assemble this, and this time to assemble has to be more than the time for fission. So you have to make sure that you have enough time that keep this together, not so that does not explode. So you have to keep it together for enough time that the fission actually happened. So this is why Chernobyl did not explode. Nuclear reactor cannot explode because it will melt and evaporate before it explodes. So you want to make sure that the time here is such that it's together for as long as necessary that fission happens. And this is another parameter. This is why plutonium bomb was a little bit different because of the problem how to keep it together you needed a little bit longer. And so this is missing time. And finally, once you solve and for this you need to calculate velocity. Tamper has two roles, and even in the modern design, tamper has not only a role to reduce the total mass of uranium, but it's made such that once the explosion starts, it keeps uranium together. So keep the pressure together so that it does not evaporate too soon. So this is another part of the bonds. And this is in more detail. So this is what they really built. As you see, I only concentrate uranium because it's much simpler than plutonium. Now you have even some numbers, the details, how big things are. These were. So from the little sketch of the bomb done in 1943, in 1945, they did this. And that's the last thing. Oh, it's not. I was at the place where they tested the bombs. It's about 70 miles north of Las Vegas. It's about 70 miles north of Las Vegas. That's me. And we are on the crater, which is called Project Sedan. It's a crater. This is the biggest bomb ever tested in United States soil. And
so who all is in that picture? Who else is in that picture?
Here on this picture is Stan Nepper, Heath Tibbs, Chester Wilson, the director of the entire system, and Cardenas and me. So we were visiting there, and they gave us a tour. But now, just for you to realize how big this is, I have the other picture, and we are standing here. So,
When was this?
huh?
When was this?
Where was this?
When?
Ah, this was Heath Tibbs was the first or the second year here at Tech.
Oh, wow.
I don't know. Stan Nepper was the dean. So that's a time.
I was here already.
So, and you can see this is where we took the picture in front of this big. And they had so many tests. As you drive, there are so many holes there. And the last picture, this is me and my wife sitting on one of the. This is where they actually tested the bomb. It's I was not exactly at the place where you find on the images because it was close, but we took picture relatively close. So this is a literature which I use. I said everything is done by other people, and it's this and other people. That's it.